So, good morning. Thanks to the organizers for the opportunity to speak here, and thanks for everybody for showing up. I'm delighted to be back at the Fields Institute. It's been almost 10 years, which is way too long. I'd like to start with, before I actually start the talk proper, I'm going to, you know how on web pages they put it in little tiny print. This is an advertisement for ICRA 2016, which I think might be of interest to some in this audience. This is the International Conference on Representations of Algebras. Will be in Syracuse, August 10 to 19 of 2016. I'm one of the organizers. There's a long list of organizers and advisors. But if you have any questions about it, I'd like to talk to you. Anyway, what I'm actually going to talk about today non-commutative desingularizations and commutative algebra. And my goal, or the aim, is to, oh, and I should apologize here at the top. I've given a talk similar to this previously, which I know some people in the audience have seen, so there will be a little bit of repetition. I'll try to sneak in some new things as we go along. The goal is to figure out how to replace the geometric idea of a resolution of singularities say we have some affine scheme, spec R, the resolution of singularities is, well, let's not worry about what it is right now, with an algebraic version, maybe I should say purely algebraic version, say R to lambda, of course the arrow is reversed, where lambda is some not necessarily commutative ring. You could hope to do it with commutative rings. We'll see very shortly that that's a vain hope. And this sentence should continue. An algebraic version with the same or close enough properties. And we'll decide what those properties are as we go along. And the guiding principle, or one of our guiding principles, in this decision process is to adopt a representation theoretic point of view. By which I mean that rather than focusing on ring theoretic properties, let's focus on the module categories, or rather, well, focus on the module categories or even the derived categories of modules, and try to make whatever properties are mentioned in the line above be properties of the module categories. So right away, one could take this guiding principle. I call it a guiding principle rather than a sort of a commandment. One could decide to strictly adhere to it. And to forget about rings entirely, commutative or not, and simply talk about functors between abelian categories or triangulated categories. If one does this, one ends up with something, or one could end up with something called a categorical resolution of singularities. First discussed by Bondal and Orlov, recently subject of significant work by Kuznetsov and Luntz. I won't bother you with the definition. It's the existence of an adjoint pair. As with all choices to strictly adhere, you end up in a monastic place. You end up in a place that's very dry. I'm going to go ahead and say that this is not particularly useful for the things I have in mind. I won't write that part because I just like making provocative statements on the board and then clarifying verbally. So instead, okay. We work with actual rings and actual modules. So let me remind you, I chose not to remind you earlier, but let me do it now, what a resolution of singularities is. So this will be my standard notation for resolution of singularities. It's a pi going from x twiddle to x, and it is a resolution of singularities of a variety x, and it is a morphism pi such that, first of all, x twiddle is non-singular, smooth. Second of all, pi is proper, which the precise definition doesn't concern us today. Let's just remind ourselves that if we're working over the complex numbers, which you all probably were anyway, this means that pi inverse of compact is compact in the complex topology. And third, that pi is birational. It induces an isomorphism on the function fields. So our game plan, is to take those three ingredients of the definition and translate them
to
theoretic properties for our desired map from R to lambda. Let's start from the bottom. It's always easiest to start from the last one. So what should it mean that a ring map R to lambda is birational? Think, if you like, that R is maybe an integral domain. Well, you could insist that it means there's an isomorphism on function fields. That would be a little bit silly, because that would force lambda to be commutative, thereby restricting far more than we want to. But in accordance with the guiding principle, we think that this birationality should be something about the module categories. In particular, we are going to identify rings that are Morita equivalent. If their module categories are equivalent, we're going to say that the rings are really the same. So rather than saying insisting that lambda have quotient field equal to Q of R, the quotient field of R. How far down can I go before you can't see Kevin or Kenneth? Is it? Okay, stop here. Got it. We ask that when you tensor with the quotient field, think of this as inverting all the non-zero divisors in R. We ask that that thing should be Morita equivalent to Q of R rather than being equal to Q of R on the nodes. And this is a field. We're thinking that R is probably a domain. The only things Morita equivalent to fields are matrix rings over the field. So we ask that lambda tensor the quotient field of R is some matrix ring over that quotient field. So that's the translation of birationality. We're going to, in fact, call that box property birationality, just for short. What about properness? Well, I didn't tell you really what properness is, but it is known, something for the Game of Thrones fans in the room, that a proper morphism between affine schemes, that is, spectra of rings, is finite. So let's go ahead and ask that our ring map R to lambda be a module finite map, that it make lambda into a finitely generated module over R. And finally, oh, I've done this now, haven't I? Oh well. What should non-singularity translate to? We should ask, this one's pretty straightforward, we should ask that lambda has finite global dimension. By the Auslander-Buchsbaum-Serre theorem, the only rings having finite global dimension are the ones corresponding to smooth points. So we'll take that one as obvious. Is this all okay with everybody so far? All right. So we arrive then at a definition. A useless non-commutative resolution of R, which is some unspecified commutative ring, is an R algebra lambda, which includes, by the way, for the technically minded, the assumption that R maps into the center of lambda. But let's ignore that for now. Which satisfies, in the reverse order we did them, first of all, that lambda is birational to R in the sense of the boxed formula in the middle board. Secondly, lambda is a finitely generated R module. And first, that the global dimension of lambda is finite.
Is of finite global dimension?
Do I mean R is? No, lambda. R is a commutative ring whose singularities we're resolving. Lambda is the thing with finite global dimension. Okay, let's see how this goes. Public service announcement. It's so tempting to write on this board, but don't do it. Don't do it. So why is this called a useless non-commutative resolution? This is far too weak. Well, reason number one, it's far too weak. Reason number two is going to be that it's far too strong. It's far too weak because any let's see how to say this. Any ring extension R contained in S with S a finitely generated R module and S a polynomial ring I should say birational. Would satisfy this. So, for example, things like any toric ring, or let me say instead, any numerical semigroup ring The problem with this is that being birational is simply not strong enough. It doesn't tell you anything about the connection between R and S. Also, I'm sorry.
Situation.
No, you're right. I went back and added that after and forgot that it killed the second half of the sentence. Okay, let me give you another reason why it's far too weak. It's far too weak because global dimension, or finite global dimension, is badly behaved. For non-commutative rings. All sorts of pathologies. Doesn't have to drop when you localize, for example. And let me go ahead and address this and not talk about the far too strong business. I can talk about that perhaps next time. Let's address this. I feel like maybe this should just work by itself. It's very high tech. So, for example, as I said, it doesn't localize well. And it doesn't, where by it I mean finite global dimension, doesn't imply Cohen-Macaulay or Gorenstein properties. As in the commutative case. So we now look to strengthen this useless definition. Try to address those failings. So we're going to impose further assumptions on our ring map to make it better behaved. So the first bullet is actually easy to address. Let's call this a definition. An R algebra lambda is non-singular if its global dimension is equal to the dimension of the ring, and actually more, let's insist that its global dimension after localizing is equal to that of the ring. for all primes in spec R. So this takes care of the first bullet. For the second, we're going to have two more definitions addressing the Cohen-Macaulay property and the Gorenstein property, respectively. Which order? Let's do Cohen-Macaulayness. Let's say that lambda is an R order if it is maximal Cohen-Macaulay as an R module. That's a replacement for being Cohen-Macaulay as a ring, which follows from non-singularity in the commutative case. And we'll talk more about these maximal Cohen-Macaulay modules shortly, which might mean 48 hours. But let me give you a couple of facts about what happens when you combine these two definitions. So facts about non-singular R orders. And for these to work, best, I'm now going to assume that R is a local ring, which in my head it always was, but now let me say it explicitly. So the first fact is that a non-singular R order is what's called homologically homogeneous. In other words, all its simples have the same projective dimension. Which, of course, is finite. By assumption. So it's well behaved in that sense. Secondly, and this is a result due to Iema and Weems, I didn't write down the year. If R is a K algebra, some field K, and lambda is a non-singular R order, then, with a finite group G acting on it, and I also should assume the order of G is invertible, then the twisted group algebra lambda hash g is also a non-singular R order. So this is a source of such things. And those of you who perhaps were at my talk at SRI a couple years ago, this is a jazzed up version of the Mackay correspondence, which, again, I'll say more about shortly, where shortly in this case means 96 hours, I think. All right.
No point in that, is there?
Third, so we're continuing with 3 additional assumptions to put on our ring map to make up for the fact that global dimension behaves badly. And I need to insert here for what I'm going to say next to be true and or useful, I need to assume that my base ring, the thing I'm resolving the singularities of, is Cohen-Macaulay. This is not a particularly stiff requirement. Examples are determinantal rings, rings of invariance, most rings you pick up at the store. So now with that assumption in place, let's talk about what it means for lambda to be a Gorenstein R algebra. This means that this thing that I'm going to call omega of lambda, that is, take the canonical module of your ring R, assume it has one, and co-induce it up to lambda if this thing is a projective lambda module on both sides. Only on one side, excuse me. Combining 2 definitions. Projective lambda module only on one side. So what does this get us? If we add this to our ever-growing list of hypotheses, well, first of all, I've got so many numbers. Let's try A now. and R order lambda is non-singular, remember this meant that its global dimension behaved well with respect to localization, if and only if it has finite global dimension and is Gorenstein. In other words, this Gorenstein property stands in for checking all of the localizations. And secondly, another nice consequence, the Gorenstein R order satisfies the Auslander-Buchsbaum formula for modules of finite projective dimension. In other words, it's another patch for the fact that the finite global dimension doesn't behave well for non-commutative rings. All right, and this should be maybe 3A or 3' or something. An additional property that will be useful this is the one I was prematurely mentioning over there. Let's say, make sure I get it right. Lambda is a symmetric R algebra if Hom over R lambda into R is isomorphic to lambda as a two-sided lambda module. So you see that in the special case where R is Gorenstein, that means that this thing is R itself. The canonical module for R is just R. Then we're talking about the same Hom module. So in particular, if R is Gorenstein, so its canonical module is free, we have that symmetric implies Gorenstein. As a bimodule, that's what I should say, yes. As a bimodule, yes. Thanks, Paul. And there should be an isomorphism here, rather than equality, of course. I don't actually know, perhaps some of the experts in the back of the room know, whether these properties are comparable without the Gorenstein assumption, or with any even slightly weaker assumption, whether symmetric and Gorenstein are comparable. Now, the reason I bring up this symmetry hypothesis to say everything I want about this, but I'll try to say something intelligible. Turns out that in reasonable circumstances, which I'll say what that actually means in just a second. The symmetry condition is equivalent to lambda having a much more understandable structure. It's equivalent to lambda being an endomorphism ring. Of some R module. So let me say more about this. So first of all, there's a theorem of Auslander from, I didn't write it down. I think it's the purity of the branch locus paper, which was 59. That, let's suppose R is a local normal domain. And M is a reflexive R module. Then the endomorphism ring, which I'm going to call lambda, the endomorphism ring over R of M is a symmetric R algebra. So what does that mean? I need to give you an isomorphism between lambda and its dual into the ring R. And, oh no, sorry, wrong way around. It goes this way, and we send F to the trace of something times followed by F, following F. So take a map from M to itself, look at the trace of a linear functional following that map. This gives you an isomorphism. In particular, of course, that means it's a symmetric R algebra. And even more, the converse holds in some situations. So this is where I'll have to skip a little bit. The converse follows from work of Auslander and Goldman. On so-called maximal orders. The name of the paper is Maximal Orders. And it says that the following are equivalent for a module finite algebra lambda over a Gorenstein now local normal domain R first, or A, let's say, lambda is a symmetric birational non-singular R order. B, lambda is isomorphic to an endomorphism ring for some reflexive R module M and has finite global dimension. And third, let's see, put it over here. Lambda is an endomorphism ring as above and to the left, and lambda is homologically homogeneous. Yes. Jason, you look pained. Is it okay? The content, the contribution of Auslander and Goldman is, of course, A to B, which says that if you have a symmetric non-singular order, a symmetric birational order, then it's an endomorphism ring. Other parts of this due to Vandenberg, who I think might be here later. Parts. So, I know it's been a lot of definitions, but here in A, you find all of them. These are all of the definitions we've discussed. That lambda should be a symmetric, which implies Gorenstein, because we're over a Gorenstein ring, birational non-singular order. And so therefore you end up with a better definition of what a non-commutative resolution of singularity should be. Let's let R be as in the middle board, so a Gorenstein normal domain. He doesn't assume local. Oh, right, do not move. A non-commutative crepant, there's a new word, non-commutative crepant resolution of R is an R algebra lambda, which is an endomorphism ring, M should be reflexive, and lambda should be homologically homogeneous.
In the you need a co-Macauliness of lambda.
Statement B, I need co-Macauliness. Yes.
of simplicity.
Yeah.
It's kind of difficult.
Okay, I'm not sure. I'll trust you, and we can talk about it after. Okay. I'll add it in, and maybe you can explain it to me later. So it needs to be in order, Osama says. I should stop at this point. What I want to talk about next time, just to give you a chance to decide whether to come or not, is what else we can do if we relax this Gorensteinist assumption, what this word means, crepent, and what a definition like this might be used for. So, thanks for your attention.
So let's take this speaker again.